Hello, welcome to our second lecture for linear algebra. Today we are going to be talking about parallel vectors, orthogonal vectors, and I will use these two to deduce equations for the line in R2, and I will do some exercises about lines in R2. So what I want basically is to determine necessary and sufficient conditions for two given vectors to be parallel, something that we can, verify very quickly or very easily. The same for orthogonal vectors. Orthogonal vectors is basically an extension of perpendicular vectors. And I will combine these two criterions to deduce two different kinds of equations for the line in R2. Okay? Before going to this, let me do a very brief review of what we did last class. So remember that we introduced Rn as a vector space. So it's not only the set Rn, we have four different constituents of a vector of Rn as a vector space. Rn is a way of talking because Rn is just the base set. So we have the base set here. Rn, remember that an element in Rn is an n-tuple. So it's an ordered list of real numbers consisting of exactly n real numbers. R, that is going to be our scalar set, and these two are the operations. The addition that takes two vectors and returns a new vector. Okay, let's say that if I'm gonna write it in a little bit more compact way. Let's say that if I add the vector x and the vector y, the ith entry or the ith component of the addition is gonna be the addition of the ith component of x and the ith component of y. Is that okay? And we have a second operation, the multiplication of a vector by a scalar, which takes a scalar and a vector in Rn and returns a new vector in Rn. Okay, so if I multiply the scalar alpha by the vector x, the ith component of this new vector is gonna be the ith component of x multiplied by alpha. And we know basically that these two operations satisfy 8 properties. That basically what these properties tell us is that these two operations are good enough. Okay, that everything that we are used to with, let's say, numbers on other objects that we have operated before stay valid here, which is gonna facilitate our life when working on a problem. So basically, let me put it this way: the addition is commutative, which means that when we are adding two vectors, doesn't matter in which order we take them, the resulting vector is gonna be the same. The addition is associative, which says that when we are adding more than two vectors, let's say 3 vectors, we can add any two of them first to obtain a partial result, which is going to be added to the third, to the one that we didn't use. And obviously this, we can extend it by induction to add more than 3, any finite number of vectors. There is a neutral element neutral element for the addition of vectors, which is the vector 0, and every vector has an opposite, or every vector x has an opposite, which is going to be minus x. Okay? The multiplication of a vector by a scalar distributes with respect to the addition of vectors, but also distributes with respect to the addition of scalars. Okay? We know also that we multiply two scalars and then multiply the resulting scalar by a vector x, we are going to obtain the same result as if we multiply the vector by one of the scalars first, and then the result is multiplied by the other scalar. Okay, and one is the neutral element for the multiplication. So every time we multiply any vector by one, the result is going to be the same vector. Is that okay? Well, these 4 elements with these 8 properties is what we are going to call the vector structure of Rn. And this is everything that we need to do algebra. In addition to this, we introduced another tool that is the dot product. And as we said, this is going to allows us to solve some, let's say, basic geometrical problems. The dot product is now a function that takes 2 vectors but returns a number, scalar, and, well, it works as follows. The vector x dot product vector y is going to be the scalar that we obtain by taking the summation from I equal 1 to n of xi times yi. Okay, so basically we are taking all the products of a component of x with a corresponding component of y, and then we add over all these products. So, okay, and we use the dot product to define the magnitude of a vector, which is the square root of that vector dot product itself. Geometrically, we know that that magnitude is giving us the distance from the origin to the ending point of that vector, and we also deduce a formula for the cosine of the angle between two vectors. The cosine of that angle, well, theta is the angle between the vectors x and y, is x dot product y divided by the magnitude of x times the magnitude of y. All right? Okay. And this is basically what we did last class. So now we are going to proceed to deduce necessary and sufficient conditions for two vectors to be parallel. Well, last class when we were interpreting the multiplication of a scalar by a vector, we saw that if a vector x is equal to alpha times a vector y, then x is parallel to y. Is that okay? And, well, here we are also including the vector 0, because if alpha is 0, x is going to be 0. And maybe in this case it doesn't make too much sense to talk about parallel, because the vector 0 is not pointing anywhere, so it's not forming any angle with y. Okay, so let's suppose for now that alpha is different from 0 and x and y are different from the vector 0, obviously, if this is happening. Okay, but what I wanna prove is that indeed this condition here is not only a sufficient condition, not only if this is happening, the vectors are gonna be parallel, is also a necessary condition. So since the vectors are parallel, then this is happening. Okay? Well, to prove that, let's consider which are the two situations in which two vectors are parallel. So if I have a vector x parallel to a vector y, this is one of the possibilities. So the angle between the vector x and the vector y is going to be 0 degrees. Or the other condition that we have is that the angle between the vector x and the vector y is going to be 180 degrees. But the cosine of 0 is 1. The cosine of 180 is -1. So in any of these two cases, we are going to have here either 1 or -1. So if I raise this to a second power, we are going to get that 1 is equal to x dot product y squared divided by the magnitude, the square of the magnitude of x times the square of the magnitude of y. All right? And basically, we are going to be using this to prove that if two vectors are parallel, so if we are in any of these two cases, then we are going to be able to find a scalar alpha such that x is going to be equal alpha times y. Is that good? Well, let's see. To prove that, we need to find that scalar alpha. So let's try to see if such an alpha exists, what that alpha would be. Well, we don't know if this is true, or if it were true, that what this alpha would be. Well, if I take this equation and I take the dot product with y in both sides, we are going to get x dot product y is equal to alpha times y dot product y. So alpha is going to be x dot product y divided by the magnitude, the square of the magnitude of y. Is that okay? So we don't know if alpha exceeds, but if it exceeds, it has to be this one. Is that okay? Or what I'm gonna do is to prove that indeed this alpha is working. That if I take alpha as this value here, x is gonna be equal to this alpha times y in any of these two cases. In the case that x and y are parallel. Is that okay? But proving that this is equal to this is equivalent to proving that x minus alpha y is equal to a vector 0. So what I'm going to do is to prove that x minus this alpha times y is equal to a vector 0. Well, it's exactly the same. Yes, but proving that a vector is the vector 0 is equivalent to proving that the magnitude of this vector is 0, because the only vector that has magnitude 0 is the vector 0. So if I can prove that the magnitude of this vector is 0, I'm proving that the vector itself is the vector 0. So this 0 is a 0 number, but the vector itself is the vector 0. So what is going to be this? Magnitude of x minus, and I can put the square here just to get rid of that beautiful square root. What is going to be this? We saw last class that is pretty similar to what we did last class. This is the vector x minus alpha y dot product itself. And now we can start distributing here, and this is going to be x dot product x. I want to put it this way, plus x dot product minus alpha y plus minus alpha y dot product x plus, I'm gonna write this, minus alpha y dot product minus alpha y. So, okay, sorry, don't have a space here, so I'll write it down. Okay, but we know that we can take the scalars out and that x dot product x is magnitude of x squared. So it's, sorry, let me say it right. Is the square of the magnitude of x. So this is the square of the magnitude of x. I will take this alpha out. So this minus alpha out, and this becomes minus alpha that multiplies x dot product y. I will take this minus alpha out, and I'm gonna have y dot product x, but that's exactly the same. So I'm gonna put a 2 here. I take the first minus alpha out, the second minus alpha out, and that becomes minus alpha squared. Y dot product y, which is the square of the magnitude of y. Is that okay? So we have this. But what is my alpha? My alpha is this here. Oh, I can replace my alpha here, and this is gonna be magnitude, the square of the magnitude of x, minus 2. What is alpha? X dot product y, but I have another x dot product y here, so x dot product y squared divided by the magnitude, the square of the magnitude of y, plus what is alpha? It's this here, so again I'm gonna have x dot product y squared divided by the square of the magnitude of y to the second power, so to the power 4th, but since I have this square of the magnitude of y, I can cancel this with this, and just the second is gonna stay. Second power here is gonna stay. Okay, so I'm gonna cancel it, and I will put a 2. Is that okay? But this is what we have so far, but we want to get 0. But to get 0, so far we are just working with this expression here. We haven't used that we are in this situation. But we already saw that this situation is equivalent, is giving us to this, because in any of these two situations, the square of the cosine is going to be 1, and we are going to get the square here and the square here. So it's giving us this formula, which in particular is giving us that the square of the magnitude of x is equal to the square of x dot product y divided by the square of the magnitude of y. So I'm gonna come here and I'm gonna write the square of x dot product y divided by the square of the magnitude of y. But notice that that's exactly what I have here. So if I combine this with this, I'm gonna have 2y's, the square of x dot product y divided by the square of the magnitude of y, and here I have now minus 2, exactly that, the square of x dot product y divided by the square of the magnitude of y, and now obviously this is gonna be 0. Okay, and our proof is complete. All right, so now basically this is not an if then. What we are gonna have is that x, the vector x, is parallel to the vector y if and only if x is equal to alpha y for some real number alpha, for some scalar alpha. And here I'm including alpha equals 0, which as I said before, so I can put it this way, or I can simply say parallel or one of the vectors is 0. I'm going to leave it this way. Is that okay? All right, so we are done with our first problem. For now, we are going to go to the second one. All right? Well, what happens now if x is orthogonal to y? If x let's say, if x is perpendicular to y. If x is perpendicular to y, we know that this means that the angle between x and y is 90 degrees. But if the angle between x and y is 90 degrees and we go again to the formula that we have for the cosine of the angle between x and y, which is x dot product y divided by the magnitude of x times the magnitude of y, what we are going to get here is, what is the cosine of 90? The cosine of 90 is 0. Okay? The cosine of 90 is 0. So, what we are going to get is that x dot product y divided by the magnitude of x times the magnitude of y, all right, is 0, but a fraction is 0 if the denominator is 0. So this means that x dot product y is 0. Obviously, so we have, if the angle between x and y is 90 degrees, the dot product of them is going to be 0. If the dot product of these two vectors is 0 and none of them is the vector 0, this formula is telling us that the cosine of the angle is going to be 0. If the cosine of the angle is 0, the vectors are perpendicular. Is that okay? Good so far? But x dot product y can be 0 if one of the two vectors is 0. Is that okay? And 0 again is not pointing anywhere, so it doesn't make sense to talk about angles between 0 and any other vector. And that's the reason we, instead of this word here, we are gonna start using orthogonal. For parallel, I won't use any different word, and I will include in 0 as well here, because it's not gonna cause any harm for us. All right, and we have here these two conditions. So x, the vector x, is parallel to the vector y if and only if there is a real scalar alpha such that x is equal to alpha times y. Okay? And x is orthogonal to y, and I'm going to have use of this symbol a little bit, if and only if x dot product y is equal to 0. All right? And now we are also done with this here. Okay? Again, I'm including 0 in these two conditions. All right? And just abusing a little bit. If I need to exclude 0 for some reason, we are gonna do it. All right. Let's have a very simple exercise now. I should put it this way: parallel, orthogonal, or neither. Okay. Our letter A. I'm giving these two vectors. X is the vector -1, 2, 0, 1. And Y is the vector -3, 2, 1, 2. Okay? B is gonna be X. I'm giving in this case two vectors in R4. Now X is gonna be 2 minus 3, and Y is gonna be 6, 4. Let's see. Now I'm giving you two vectors in R2. Now X is gonna be 3, 3, 3, 3, 3, and Y is gonna be -1 over 9, -1 over 9, -1 over 9, -1 over 9, comma, -1 over 9. These two vectors are in R5, and all we need to determine whether they are parallel or orthogonal or neither. Is that okay? Well, parallel in this case. Well, to be parallel, this vector needs to be this one times some scalar alpha. Is that okay? Well, if I want to make this equal to alpha times y, in particular, I need that alpha satisfies -1 is equal to alpha times -3. Because how do we multiply a scalar by a vector? Multiplying every component of this vector by alpha. And if these two vectors are equal, the corresponding components needs to be assigned the same value. So the first component of alpha times y is going to be alpha times -3, and needs to be the first component here. So this equation needs to be satisfied with this telling us that alpha is equal to 1/3. If some alpha work, it has to be 1/3. But obviously now the second component are the same. So alpha equal 1/3 is not working anymore. So also we need 2 equals to 2 times alpha, but the alpha that we need now is 1 and not 1/3. And we need to find one value, one scalar working for all the components at the same time. Is that okay? So obviously component, we take the same components unless one of the components is 0, that we need to make an arrangement. Independently, we are going to be able to find alpha, but the alpha that we need to find needs to work for all the components at the same time. Such an alpha doesn't exist because the one that we need for the first component is 1/3. The one that we need for the second component is 1. So the same component, the same alpha is not working for all the components. So parallel, no, the condition for parallel is not satisfied. Is that okay? So let's see orthogonal. Or orthogonal, we need to compute the dot product. Dot product of these two. It's dot product y is equal to 3 plus 4 plus 0 plus 2, which is giving us 9, different from 0. So this condition failed. This condition also failed. It's not neither parallel nor orthogonal. That means that the angle between these two vectors is neither 0 nor pi nor pi/2. Is that okay? Is that good? If you want now, so this exercise is just asking for us to determine if the vectors are parallel, orthogonal, or neither. In this case, the answer is neither. But let's say that we want to find the angle. Well, we have the formula for the angle, and we can determine the angle between these two vectors. What we know so far is that that angle is not 0, that angle is not pi, and that angle is not pi over 2. Good? What about letter B? All right, letter B. Okay. Well, let's say if x is equal to, let's see if x is equal to alpha times y. Oh, looking at the first components, that means that alpha needs to be, again, 1 over 3. 1 over 3. But 1 over 3, if we multiply 4 by 1 over 3, that is the scalar that we need to multiply by 6 in order to get 2. If we multiply 4 by 1 over 3, we won't get negative 3. So again, such an alpha is single scalar working for all the components doesn't exist, so they are not parallel. But let's compute now the dot product to see if they are orthogonal. Now we have 2 times 6, which is 12, plus negative 3 times 4, which is negative 12, and now it's 0, which is telling us that these two vectors are orthogonal. All right? And, in the last case, let's see. Is there any alpha that multiplied by y gives us x? Okay. Well, to get through here, what is the number that we need here? What is the number that we need here to get through here? Well, the alpha that we need here is going to be negative 27. If alpha is negative 27, negative 27 times negative 1 over 9 is going to give us 3. But if we multiply now that alpha by the second component, since all the components are the same and all the components here are the same, this is working for all the components. So in this case, the two vectors are parallel. Okay? Good so far. So it's clear how do we use these two criteria here. All right. So let's see how we can use it in a little bit more complex scenario. Let's suppose now that we want to determine a line, that we want to determine an equation for a line R2. Okay? So if I tell you what do we need to determine a line, an equation for a line, you're gonna most likely at this point you're gonna tell me I need 2 points or I need 1 point and the slope of the line. But since we are working with vectors, I want to use vectors somehow. So what we are gonna do is describing lines using vectors. All right? Well, what happens if I want an equation for this line here? The line L. What do I need? Oh, I will need a point. Let's say at 0, y0. But 1 point doesn't suffice. The other thing that I'm going to use is one vector. Okay, let's say the vector x, and I will denote the first component as letter A and the second component as letter B. So it's a fixed vector. And this vector, what is the relation between the line L and x? I will say that L is parallel to the vector x. Is that okay? All right. So basically, if I translate if I translate the line to the origin, that line is gonna fall on top of this vector. Is that okay? Or in other words, what is happening? What is the meaning of this? That means that if I take any other point x, y here, all right, and I consider the vector whose components are the same as the components of the point P, and the vector, another vector whose components are the same as the components of the second point that I'm considering, okay, this vector minus this one, I know that is gonna be, if I put it here, it's gonna be over the line. Is that okay? So basically what this means is that any point that I choose, any other point that I choose on the line, is that okay, is producing, if I consider the corresponding vectors, the subtraction is gonna be parallel to this one here. Is that okay? But what is this vector here? Well, this vector here is x minus x0, comma, y minus y0. And basically this vector must be parallel to the given vector x. And this is going to be the first equation that we have for the line, because now we know that two vectors are parallel. If two vectors are parallel, it's because there is alpha real such that x minus x0, comma, y minus y0 is equal to alpha times x, which is a comma b. And notice that if this point is the given one, is x0, y0, this vector is going to be the vector 0. And that's the reason I'm including alpha here, just for working with everything together and not considering that case as something apart. That's okay? All right. And what is this giving us? This is giving us x minus x0 is equal to alpha times a, y minus y0 is equal to alpha times b, where alpha is real. Is that okay? And basically the first equation that we have for the line is, we can keep it this way. X comma y is equal to alpha, let me put it this way, x0 plus alpha a comma y0 plus alpha b, or I can put it this way, x is equal to x0 plus alpha a, y equals to y0 plus alpha times b, well, where alpha is a scale. Is that okay? And this is my first equation for the line, which I'm going to call the parametric equation of the line. Why parametric? Because we have a parameter alpha here. Is that okay? Is that good? All right. All right. What do we know here? Well, what is the given? We need to know one point at 0, y0, and we need to know a vector parallel to a line whose components are a and b respectively. Is that okay? This is what we know. This is a parameter, and xy is a free point. It's the one that I want to verify if it's on the line or not. Is that okay? When a given point is gonna be on the line, when I am able to find a scalar alpha such that these two equations become identities. So these two equations are satisfied. If I put a point here and I cannot find one scalar alpha satisfying both at the same time, that point is not going to be on the line. Is that okay? Why? Because if that point is not on the line, the vector that these 2 points are determining is not going to be parallel to the given one. Is that good? So let me put an example. Find. It's a parametric equation. Find the parametric equation of the line passing across the point 2, 3 and parallel to the vector negative 7, 1. Okay, this is pretty easy. Choose the one that you prefer. I will use the second one, and this again. X, Y. What is X? What is X0? This is X0, this is Y0, this is letter A, this is letter B. So XY is equal to 2 plus alpha times A, which is negative 7, so minus 7 alpha, and Y is equal to Y0, which is 3, plus alpha times B, B is 1, so plus alpha, and alpha is an real number. This is the parametric equation of this line. Is that okay? We'll leave it that way. No problem. And now I'm gonna go. I will say, is the point negative 1, 3 on this line? Well, let's see. Now this is your X and this is your Y. That's the reason you don't put anything here, because this is to verify if any point that you want is on the line or not. So you put those values here and you verify if you can find the same value for alpha, satisfying both equations at the same time. If you can find that alpha, the answer to this question is going to be yes. If you cannot find such an alpha, the answer to this question is going to be no. So let's say minus 1 is equal to 2 minus 7 alpha, and 3 is equal to 3 plus alpha. So the second one is forcing alpha to be 0, but if alpha is 0, we get negative 1 equal to, we know that it's not the same. So there is not scalar alpha satisfying both equations at the same time, so no. The answer to this question is no. Is that okay? Well, let's verify another one to see what happens. Okay. What happens if I give you the vector, the point minus 5, 4. If I give you the point minus 5, 4, so we repeat the same procedure. Now the given point is minus 5, 4, so we will here we say minus 5 equals to 2 minus 7 alpha, and 4 equals to 3 plus alpha. But again, the second equation, use whatever you want. I'm using the second. The second equation is giving us that alpha must be 1. If alpha is 1, 2 minus 7 times 1 is 2 minus 7, which is negative 5. So both equations satisfy for alpha equal 1, or alpha equal 1. So the answer in this case is yes. So you see, it's pretty simple. It's pretty simple. Okay. But what is the interpretation of this alpha? What is the interpretation of this alpha? Okay, let's interpret this a little bit. So now we know how to get this equation in a specific problem and how to use that equation. We can use that equation for what kind of problem? So this is one of the problems that we can for which we can use this equation to verify if a given point is on the line or not. All right, we already did. The other thing that we can, there are obviously other problems for which we can use this equation. This equation is giving us a lot of information, all the information that we need about the line. But talking about the very basic problems that we can solve with this equation is we can verify whether a given point is on the line or not. And the other thing is we can generate as many points on this line as we want. How? Let's say that I tell you, oh, give me 5 points. Give me 5 points on this line. Okay. What I'm gonna do is add y. I need 5 points. So, and I know that y depends that x and y depend on the parameter alpha. So what I'm gonna do this way, what I'm gonna do, okay, give me 5 points on the line. Okay, what I'm gonna do is assigning values to alpha. Alpha equal 1, what I'm gonna get? 2 minus 7 minus 5, well, the one that we got here. 2 plus 1, 4. And I have my first point. Alpha 20, what I'm gonna get? 2 minus 140 minus 138. 3 plus 20, 23. I got my second point. So I can get as many points as I want, just assigning value to alpha and using the equation. So the two basic problems that we can solve with an equation is verifying if a given point is on the line or not, or generating as many points, getting as many points on that line as I want. Is that okay? All right. Okay, so now let's interpret this equation a bit. What is happening here? So notice that we have our line L, we have a point P, which we said is a 0, y, 0, and we have a vector x that is parallel to the line. So what is the meaning of that alpha that we are finding? So every time we have another point, x, y, it's common. So remember, I'm so very sorry, but remember this is a capital letter and this one is gonna be a lowercase. Is that okay? So we think of that alpha is the following. If we put that vector x here, okay, exactly that vector x. So sorry if the magnitude is not exactly the same or something. Forgive me. It's exactly the same thing. Okay. What alpha is telling us is the following. If this point is on the line, we can repeat this x a real number of times until we reach that point. That's the meaning of alpha. So xy is here. Or let's say that this is x again. We are repeating this vector 2 times. So basically the magnitude of this vector, we can think of it as the unit of time. So alpha is basically the time, and this given point is like the origin on the line. So this alpha is basically what is the amount of time that we need for our origin to reach that given point, thinking of the unit of time as the magnitude of the vector x. Is that okay? So in this case, it will be 2. But what happens if with the sign of alpha? The sign of alpha is basically telling us if we are moving in the same direction of the vector x or if we are moving in the opposite direction. Is that okay? Look at the following. So this, we can think of this point of this vector as the vector connecting 0 to the point P. So when a given point is given, we have a line passing across the origin. When we multiply x by a scalar, what we are doing is just changing the magnitude of x. Yes or no? We already know that. So we are moving like along a parallel line. Okay, so if we take this vector and we move it here until this point becomes the given point xy, so this here is gonna be a vector parallel to x. So to get this vector, we just need to multiply x by some alpha. Well, whatever movement is occurring here is the same thing here. So that's the reason alpha, we can think of it that way. That's the reason alpha needs to be the same for both equations. Is that okay? All right. Okay, so now, again, and we are going to be doing this all the time. So all the time we are going to be working algebraically, but also assigning a meaning to every algebraic procedure that we apply. All right. Okay, so I'm going to keep it pretty simple today. I will deduce a second equation for the line. What is the other way in which we can describe a line using vectors? Well, let's suppose that we have our line L here. Again, we have our point P at 0, y 0. And now instead of a parallel vector, what we are going to have is I'm going to put it here, an orthogonal vector. It's a normal vector. A normal vector. So let's suppose that this vector, I'm going to call it N, and let me use PQ as the components of this vector. Is that okay? What is going to happen now when we have a point xy on the line? Well, we already know that if we consider this vector connecting the origin to P, and we consider this vector connecting the origin to the point xy, this vector minus this one is going to give us a vector that is parallel to the line. So x minus x0, y minus y0 is going to be parallel to the line L. But N is perpendicular or orthogonal to the line L. N is, perpendicular to the line L. Is that okay? But if N is perpendicular to the line L, and L is parallel to this vector, N is perpendicular to orthogonal to x minus x0, y minus y0, which is telling us that the dot product of these two vectors is 0. Is that okay? It's 0. Well, this is giving us that P comma Q dot product x minus x0 comma y minus y0 is equal to 0. And this is P times x minus x0 plus Q times y minus y0 equal to 0. And this is the normal equation of the line. Normal equation of the line, and this is the equation maybe a little bit more similar to the one that you have studied before, y equals to mx plus n or plus b, whatever symbol you use for that part. Is that okay? Obviously, I can work here a little bit. I have that y minus y0 times q is equal to I will suppose q different from 0, and obviously this equation is not describing all the lines. This equation is never describing which line is not described here. Which line is not described here? Which line doesn't have a y? Think a little bit about that. Which line doesn't have a y? Well, what happened with the vertical line? What is the equation of this vertical line? X equal, let's say, 1. So the value of y doesn't matter, because every point, what is the condition that every point in a vertical line satisfies? That its first coordinate is equal to 1. Is that okay? So in this kind, in a vertical line, we don't have any y. Is that okay? Is that good? So this is not this is describing all lines that are not vertical. In my case, that means that q is different from 0, in which case I can write this as y minus y0 equals to minus p over q x minus x0. Y is equal to minus p over q x minus x0 plus y0. Is that okay? Well, if you want minus p over q x plus p over q at 0 plus y0, if I call this m and I call this n, I have exactly the equation. Is that okay? So the equation of the line are this way or this way. And well, if q is 0, that's exactly what I'm going to get. It's equal to a constant. I put a different value here just for you. So I put that 0 here. You will say that I'm not obtaining the same. Okay? So basically, this is more similar to the one that you obtain. Indeed, you call these maybe in previous courses the standard form or the standard equation of the line. So what I'm going to call it normal because I'm making emphasis on the fact that these two numbers here are the components of a vector that is orthogonal to a line, and normal always means orthogonal. Is that good? All right, so I can give you very similar exercise. What happens if I say now, instead of parallel, orthogonal or perpendicular to this vector? Oh, now it's not the same equation, it's not the same line. Okay? But what I'm gonna do is, oh, now this is PQ, and what I'm gonna do is P times x minus x0. Is that okay? Plus Q y minus y0 needs to be 0. So minus 7x minus 2 plus 1 times y minus 3 is equal to 0. Okay? So minus 7x plus 14 plus y minus 3 is equal to 0, which I can keep as minus 7x plus y plus 11 equal to 0. You can solve for any variable if you want, whatever you want. That's good for me. Is that okay? Same thing. How can we use this equation? Just for simple problems. I can use the equation to verify if a given point is on the line or not. When I plug the value of x and the value of y here, where x is the first coordinate of that point, y is the second coordinate of that point, this equation needs to become an identity, so the equation needs to be satisfied. Or I can use it to generate as many points on that line as I want. Is that okay? Is that good? All right, these two exercises are pretty simple. I can give you, obviously, a little bit more complicated exercises. So, as I said before, I'm doing all these just because you see these are very simple ways in which we can use vectors. And I also plan to exploit the geometry behind all the algebra that we are going to be doing. Is that okay? But in several courses of linear algebra, you won't see this part. Okay, so we have the parametric equation. Which is x equal x0 plus a times alpha, y equal y0 plus b times alpha. Alpha is real. And we have here x0, y0 is a point on the line. AB is a vector parallel to the line. Okay, alpha is the parameter. And we have the normal equation of the line, which is p times x minus x0 plus q times y minus y0 equals to 0. And now here, PQ is perpendicular to the line, okay? And again, at 0, y0, a0, y0 is a point on the line. For every line, we can get the parametric equation or a parametric equation and a normal equation. Is that okay? So let's say that this is the parametric equation of one line and this is the normal equation or a normal equation for the same line. What can we say? Well, obviously, if we are describing now the same line, this vector, same line, this vector AB is parallel and this vector PQ is perpendicular to the line, orthogonal to the line. Is that okay? Oh, this vector needs to be orthogonal to this one. So in the case that these two equations are describing the same line, PQ dot product AB is 0. Is that okay? In one case, we are using parallel information. In the other case, we are going to be using orthogonal information. And that's the idea that I want that you to keep in mind, because these, we are going to be using it during the whole course. Is that okay? All right. Let me give you one more exercise and we are going to finish with that. So exercise, find the parametric equation I will finish now with this exercise. I will do one more observation. Find the parametric equation of the line passing across the point 1, 2, parametric, and orthogonal to the vector 3, -5. So, okay? So notice the difference. In my two previous exercises, I provide you with exactly the information that you need. So the only thing that we did to solve the two previous exercises was take this information and plug into the equations. Yes or no? But now I'm complicating the things just a little bit because what you need to get the parametric equation is not exactly what you have. Because to get the parametric equation, what you need is a point that you have it, but a parallel vector. And the vector that you have now is not parallel to the line, it's orthogonal to the line. And that's the problem. So what we need to get this equation is a point and a vector that is parallel. You don't have that. What you have is a vector that is orthogonal. Okay, so far what we can say is our equation is this way. 1 plus A alpha, 2 plus B alpha, alpha real. And what you know is that this vector, since it's parallel to your line, and this one is orthogonal, this vector times this one must, dot product, this one must be 0. Is that okay? Oh, okay. So to get what we need, we just need to solve this equation. 3A minus 5B must be equal to 0. We get here that 3A over 5 is equal to B. So let's say that I put A equal 5, B is going to be equal 3, and nice. And now we can conclude that the equation of the line is going to be 1 plus, we have A now, 5 alpha 2, we have b now, plus 3 alpha, alpha real. And now we're good. Is that okay? So how can I complicate this a little bit? All by providing you with information that is not exactly what you need. Is that okay? It's not exactly what you need for the equation that I'm asking you to find. Is that okay? And I can do that in several ways. We are going to do more exercises later. The other thing, the last remark that I want to do here is the following. How can I pass from one equation to the other? Well, one thing is this, using this relationship here, which is pretty easy. But if you have the equation itself, have this equation here, something that you can do also is solve each equation for alpha. So this is giving me x minus x0 over a is going to be equals to alpha. Okay? Obviously, I can do that if a is different from 0. And alpha is also equal y minus y0 divided by beta. If alpha is 0, this is a vertical line. If a is 0, this is a vertical line, because basically this is telling us all points in this line have the same first component. Well, that has to be vertical. If b is 0, y is equal to y0, which means that the line is horizontal. So either a or b equal to 0, is that okay? We are in these two very specific case, vertical lines or horizontal lines. Is that okay? Or well, in any other case, for any other line that is not vertical or horizontal, this is going to be possible. And, well, in that case, it's super simple. And now if alpha is this and beta is this, we are going to have x minus z0 over a is equal to y minus y0 over b. Oh, this is something that you can do as well. As I said, you can exploit this relationship between the parallel vector and the normal vector, or if you prefer, you can work this way. Okay? If you have this equation here, which we saw, in general, you can put it this way, okay? By just working algebraically here and solving for y. But now to get the parametric equation, something that you can do. Also, you can use this one just to pass from a normal vector to a parallel vector with the point that you have. You already have that equation. Or you can put it this way if you prefer, or maybe you already have it this way. And you can put like x equal alpha, and y is going to be then n plus m alpha. And now alpha is real. It's a way of introducing, another way of introducing a parameter. Is that okay? Well, it's up to you. All right. I will stop by here. Thank you. Thank you very much.